Welcome back, everyone. In this video, I'm going to go over some extra practice problems dealing with electron configurations and periodic trends and reactivity. So, what I would like you to do first, actually, is to pause the video, try these problems on your own for each one, and then come back and I'll walk you through a solution. Welcome back. So, for this first question, we want to determine which of those electron configurations would represent an excited state for a neutral fluorine atom. So, how do you solve this? First thing to do is to recognize that if we have a neutral fluorine atom, that we should have 9 electrons. So, one easy way to eliminate some possibilities is to look for configurations that have a different number of electrons. And indeed, you can rule out D and A, because they each have 8 electrons. Then we need to consider, what does it mean to have an excited state or not? An excited state is one that could either violate the off-bow principle and or Hund's rule. If it violates the Pauli exclusion principle, then that is not an excited state. It's not a possible electron configuration, in fact. So, B is an excited state. It violates the off-bow principle. And we can tell because this electron here is in the 3s orbital when there's still unoccupied orbitals in a lower electron subshell. C represents the ground state, and that's because it has electrons all in the lowest occupied subshells. Now you might ask, how could this be the ground state when this has an opening but these ones are filled? Remember that for a given subshell, all orbitals are degenerate. So this 2p orbital on the left is the same energy as the 2p on the right, which is the same as the 2p or in the middle as that on the right. And so it doesn't matter which one we say we've filled up first. Okay? And then E, hopefully you recognize this violates Pauli exclusion principle. Now it also violates Hund's rule. However, because it violates the Pauli exclusion principle, in addition, it is not possible. Okay, so that is the first one. And just as a reminder, violations to Pauli exclusion principle are not allowed. However, violations to off-bow or Hund's rule are allowed, and we call those excited states. Which of these represents the lowest energy electron configuration for an atom with the indicated number of electrons? So, go ahead and pause this one and try this on your own first. Welcome back. So let's talk through these. For A, we want to know, is this the lowest energy configuration for what is being depicted? We can see that all of the lower energy subshells here in A are occupied, which is good for lowest energy. However, here we have doubly filled 2 sets of orbitals when we could have had a single filled orbital in one. Excuse me, let me fix that there. Up, 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 and remove one of the down arrows. There we go. That makes more sense. So we should have done that. So because it doesn't, it violates Hund's rule and is therefore excited. For B, it's looking good going from left up through the 2p. However, this right here is a violation of the off-bow principle. We should have completely filled up the 3s subshell before starting to fill the 3p, and so that's an excited state. The third one, you can see that the third one here is fine, and it even has just one double filled and then some single filled. However, look here, we have a violation of Hund's rule because we did not have electrons all in the same direction spin before starting in the new direction. So we have 2 up and 2 down when there should be either 3 up and 1 down or 3 down and 1 up. For D, this one is the ground state. Remember, just because this is on the left does not mean we have to fill it first. They're all within the same subshell, therefore they are degenerate. And then finally, this one is impossible. Hopefully you see here that we have 2 spins that are in the same direction in the same orbital. That's a violation of the Pauli exclusion principle and is therefore impossible. Okay, let's try problem number 3. Pause this and try this on your own first. So we want to know in this problem, what's the maximum number of electrons that have a quantum number m sub L of 0 in the ground state of sulfur. So to determine this, first what I would do is write out the electron configuration of sulfur. After we have that, we can determine the electron or the orbital diagram. And we want to know which ones have an m sub L value of 0. Well, remember, the n value is depicted here. Okay? Our L values are here. And then the m sub L value is represented by the box itself. For an s orbital, we can only have an m sub L value of 0. And for p orbitals, we could have 0, -1, or +1. And because these are degenerate, it doesn't matter which one I label as which. So I could label them as 0 on the left, 0 on the right, or 0 in the middle. The only time that it matters is when I'm counting up the number of electrons. And in this case, I want to know what's the maximum number of electrons that could have an m sub L value of 0. So if I count this up, I would have 2, 4, 6, 8, 9 electrons. However, if I had said that the middle orbital was 0 instead, then I could have a scenario where I have 10 electrons. And so in this case, there could be a minimum value of 9 and a maximum value of 10. Last question. Pause this and try this on your own. Welcome back. So we want to know which of the following elements would we expect to behave similarly to each other. Remember, when we look at the periodic table, they're organized into families, which are the columns, and they're organized into periods, which are the rows. The properties occur periodically, which is why we call it a periodic table, and it occurs only so often as we get back to the same family. So elements in the same family have similar properties. So what you would want to do is categorize them by their family. Fluorine and iodine are here in the halogens, and since they're in the same family, they would behave similarly. Carbon is right here, and then lithium and rubidium are in the alkali metals here, and make sure I don't tell you a lie, here. So elements in the same families behave similarly. Fluorine and iodine are, and lithium and rubidium are, so they would have similar properties. Carbon would not behave similarly to any of those elements. That's it for this video. Thanks for watching, and have a great day.